There's one single image physicists point to as the strongest proof of dark matter: a collision between two galaxy clusters called the Bullet Cluster. For decades, it was called undeniable. But in 2026, a team of scientists recalculated that same collision from scratch, using new data from the James Webb Space Telescope. And the numbers came back wrong. Not slightly off. Wrong enough that the one image holding up 90 years of searching may never have proven what everyone thought it did. So, if the strongest evidence we had was never really evidence at all, what exactly have we been looking for this whole time? To understand why dark matter entered physics at all, we have to go back to 1933. A Swiss astronomer named Fritz Zwicky was studying a cluster of galaxies in the constellation Coma Berenices. He measured how fast individual galaxies were moving inside the cluster and tried to calculate how much mass would be needed for gravity to hold them together. Instead of flying apart, the numbers didn't add up. The visible mass, stars, gas, dust, was hundreds of times smaller than what the math required. Zwicky called the missing mass dunkle Materie, dark matter. At the time, it sounded like a curiosity, almost a joke. Most of his colleagues simply ignored the calculation. Nearly 40 years passed before anyone took the problem seriously. In the 1970s, American astronomer Vera Rubin was studying the rotation of spiral galaxies and found the same mismatch, only far more convincing. Stars at the outer edges of galaxies were moving almost as fast as stars near the center. By the ordinary laws of physics, that's impossible. The farther you get from the center of mass, the slower the motion should be. There was only one explanation left. Every galaxy had to be surrounded by an invisible cloud of mass, far larger than the galaxy itself. From that moment on, dark matter stopped being a curiosity and became the foundation of modern cosmology. By current estimates, ordinary matter, everything we see, everything we touch, everything stars, planets, and we ourselves are made of, accounts for only about 5% of the universe. Roughly 27% more is that same invisible dark matter. The problem is, in 90 years, no one has ever seen it directly. Not a single particle, not one direct trace, only the gravitational shadows of something that, presumably, is there. But physicists had a theory about what that invisible mass should be made of. A new kind of particle. One that had never been detected, but should, in theory, exist. And so began one of the most expensive hunts in the history of science. If dark matter is real, physicists reasoned, it had to be made of particles. New ones, never detected, interacting only weakly with ordinary matter. They called them WIMPs, weakly interacting massive particles. And so began one of the most expensive, most relentless hunts in the history of science. Detectors were built in the quietest places on Earth, nearly a mile underground in old gold and nickel mines, where the sheer mass of rock overhead blocks out almost all cosmic radiation that could fake a signal. Tanks holding hundreds of kilograms of ultra-pure liquid xenon, cooled to extreme temperatures, waited for decades for a single collision. The moment a dark matter particle might clip a xenon atom's nucleus and leave behind the faintest flash of light. One of the most sensitive of these instruments, LUX-ZEPLIN, operates in the Homestake mine in South Dakota. Its rival, the Xenon experiment, runs underground at the Gran Sasso lab in Italy. Both have spent years watching, millions of hours of runtime, tens of millions of dollars in funding. And the result? year after year, is the same. Nothing. Not one confirmed collision. Not a single particle. Every year, the detectors grow more sensitive, and the place where WIMPs could theoretically be hiding keeps shrinking. Some physicists have started saying it out loud. Maybe we're hunting the wrong particle. Maybe we're hunting a particle that doesn't exist at all. Which means physicists may have spent 90 years building the entire foundation of modern cosmology on something that was never actually there. And if the particles aren't real, then whatever Zwicky and Rubin actually saw was something else entirely. Something we still don't understand. And right now, as the hunt for the particle runs cold, an idea physicists dismissed as heresy for almost 40 years is quietly working its way back to the surface. The collision known as the bullet cluster was, for decades, the strongest evidence for dark matter. In 2006, the image seemed to show it plainly. The invisible mass passed straight through the collision almost undisturbed, as if ordinary matter and something invisible never noticed each other at all. But in 2026, a team led by Professor Pavel Krupa at the University of Bonn recalculated the same cluster using new data from the James Webb Space Telescope. The amount of stars and heavy elements turned out to be nearly double what was previously assumed. Enough of an increase that the invisible mass, which had anchored this theory for 20 years, is no longer strictly necessary. If Krupa is right, the image once called irrefutable never actually proved dark matter existed. It was simply miscounted, which means M-OND, the alternative gravity theory physicists had considered nearly closed, is back on the table. But neither side of this argument has won. WIMPs were never found, but never disproven either. MOND explains galaxy rotation almost perfectly, yet struggles with certain clusters. Maybe both sides are partly right. Some of the missing mass really is invisible matter, and some of the discrepancy comes from us simply misunderstanding gravity at the largest scales of the universe. 90 years ago, Zwicky just noticed the numbers didn't add up. Today, the sharpest telescopes and the most sensitive detectors on Earth still can't say exactly what's missing from the universe, matter or understanding. If mysteries like this keep you up at night, subscribe. This channel exists for exactly these moments where science runs out of answers. For now, 95% of the universe remains either dark or simply not understood. Call it whatever you like. And maybe the discovery that changes everything hasn't been made yet.